All right, lesson 28, quantization of energy and light. Okay, so what we're getting into here is quantum theory or quantum mechanics, right? This is kind of, we've actually already been kind of doing it up until now, but this is kind of the point when they started to think that the things at the very, very small level behave differently. They actually behave a little different than we think they would, right? So here's the next part of the story. So next term to go over is something called Blackbody radiation, and it's worth talking about a bit about what this even means when we say Blackbody radiation. It sounds super confusing, but what it is just saying if you get something like a star or anything actually. So let's say like a star though, it emits light, right? So it's emitting light from it, and as something gets hotter and hotter, it emits more and more light, right? That's kind of the basic idea behind it. And the reason why it's called black body radiation is because we're assuming that if this, like most things reflect light, right? So if something comes in, some light will hit it and then reflect, right? Light reflects off me, it reflects off really everything. But what they're saying is if you had some object like a star that was like that was perfectly good at absorbing all that energy, and then it would just re-radiate it from inside the object or from the object itself. So it's pretty much saying all of the energy that's coming from some star or some object, whatever it is from the object itself. Okay, so it's not like reflected from something else, right? So that's what we mean by black body radiation. Okay, all right, so now that we have a general idea of what we mean by black body radiation, here's what they were discovering with these curves. Now let me just kind of go over what this curve is showing here. So this is called a black body radiation curve. You might have actually seen this picture before in Science 9. Like I know I've done this with some of you guys, or I guess it wouldn't be your class, it was a class before. But in the space unit, this is generally the way that stars look, right? Actually, and this would be something like our sun would be about this hot, right? That's at 6,000 Kelvin, okay? So what this is showing, you can see on the bottom, we've got wavelength. And on the left, on the y-axis, we've got intensity. So if we had something like our sun, it is putting out most of its wavelengths, right? If I had like a line drawn from like here to here, right? That's in the visible spectrum. You can see that most, like the area under the graph here, so most of it is being put out in the visible range, right? So that's all, and that makes sense, right? That's our sun, right? Is going to be putting out most of its wavelengths in the visible range, okay? But then if we had something like a cooler star, like some kind of like dwarf star, then it's going to maybe be like, half as hot, like 3,000 Kelvin. Well, what happens is that the peaks of these guys, so the peak of like our sun and the peak of this red dwarf star are shifted. You see how this one's like shifted over to the right more, which really just means that this red dwarf star is putting out most of its wavelength in the infrared range, right? So most of the light coming off of this star is in the infrared. You've got some, right? You've got this area over here that's coming off in the visible range. And that's why we still kind of see it as red, because if you think about it, red is over to this side of the spectrum, and we have more of it in the red, right? So we're going to see that thing as being red, right? But most of the light that's being radiated off of like a red dwarf star is all going to be invisible to us, right? We can't see infrared, but most of it will be all over there. And then you'll have a whole bunch, even more like into the radio wavelengths and all that kind of stuff over this way. And then you're really not going to have any kind of like, gamma radiation or any of that kind of stuff, right? Where if you're thinking about our star again, right? So this is our star, then we're seeing everything, right? Most of the light is right in the middle of our spectrum. So we're seeing that as, well, kind of all of the colors, right? So that's actually why our star looks kind of white to us, right? Kind of white or kind of yellowy. It's because it's like a mixture of all of the different colors of the spectrum in kind of even amounts, right? Most of the light is in like the middle section of our light spectrum, but That's why it's like a mixture and we just kind of see everything there. Now, this is the case for any object that you heat up, right? So this is what happens if you heat it up, let's say like iron or something, right? It starts to glow. It starts to give off its own little curve. That curve, if you're heating up iron, might be something like, well, it'd be something like one of these too, right? Where it starts to glow in it, and it's just because it's like shifted into our spectrum, we can see it now. So the hotter and hotter something gets, the brighter and brighter it gets, right? But let's say if we had a star that was even hotter than ours, well, that one would actually have a peak. So it would go up here and then like down or something. And actually most of its light would actually be in the ultraviolet range, right? And actually it wouldn't be as clear to us. Most of it would be invisible because it's on the other side now of our visible spectrum. Okay. All right. So that's a little bit of black body curves. And that's a bit more from like an astronomy standpoint. But at the time, here's why this was important to the physicist, because they were looking at this curve. They could do this empirically and get this data. When you heated something up, this is what you would see, right? Well, here's the problem. Okay, so if we start thinking about this curve from a classical physics approach, right, then what should actually happen? I'll kind of cut to the gist here. What should happen is actually this, right? So as something gets hotter and hotter, it should actually like go into infinity that way. It never should drop back down again. And this is actually what they're going to call the ultraviolet catastrophe, because nobody knew how to handle it. And here's why they thought it was that way, right? So it's really like in this paragraph here. So we're saying not only did classical physics fail to explain the relationship between temperature, yada, yada, yada. It says, so a hot object, according to classical physics, emits its energy most effectively at short wavelengths, is what the theory suggested. So if that's true, then what should have been happening is that if you heated something up, it wanted to emit its light at these like really short little wavelengths over here. That's like where it could do it the most easily. So then that's what's causing these predictions to like come way up to here. And that's not actually happening in reality, right? And everybody knew that. That's not what actually happens. So this is a case where they've got a theory, right? You've got like Maxwell's theory and classical mechanics or classical physics that are suggesting this curve, right? But in reality, they're seeing this curve. Well, they got to modify their theory, right? So this is where physicists were trying to fix what was going on. They're trying to make a better theory to like figure out why is this happening, right? So along came Planck, right? He's going to be one of the main physicists in our story. And here's what Planck suggested, right? And here's what he did. He actually just started kind of playing around with the math, trying to figure out something that would make this curve happen. So he said, well, that curve would happen, according to his math, if we suggested that energy, so the energy that's associated with heating up this object, can only happen in discrete amounts. And just like discrete means like individual amounts, right? Like little packets of energy. This is quantum mechanics, right? This is the beginning of it. So he's saying that energy itself is quantized, so he went on to say, so E is equal to HF, where H is going to be something called Planck's constant. This is on your formula sheet, but it's written this way. And then the formula is, well, really this. E is equal to N times Planck's constant times the frequency of light that's emitted there, right? So what N stands for is your numbers, right? So it's like countable numbers. So this is where the discrete part of it comes in. So N could be equal to any integer. So it's like 1, 2, 3, 4, 5, any integer from 1 to infinity, right? So that's that discrete bundle I was talking about. And then H is a very, 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 10 to the negative 34. So very tiny number, but it is a number, right? So it only happens, like these little bundles only happens. This would be like 1 times this little tiny number times this wavelength, right? So some little packet. and then 2 of those, or 3 of those, or 4 of those. Another way of thinking about that is actually thinking of like energy itself as being these little packets of energy. So you can think about like this packet of energy as being like, you know, having a certain energy, like maybe that's like energy 1. And you can have 2 energy 1s, or 3 energy 1s, or 4 energy 1s, but you can only have a discrete amount of those things. Okay. Another, you could also say it like this, right? That you've got, you know, these are HFs, right? Planck's constant times the frequency, and the frequency can change. You can have any, whatever frequency you want, but once you have that certain frequency, they come in these discrete little packets. Okay. So thinking about this again, thinking about our picture here, if I zoom in here, here's how you can kind of think of it. So if I just break this thing into chunks, I think it'll make a bit more sense here. And let's say, so this is like our visible wavelength here, right? So in our visible wavelength, you can think about this as being, we've got these, you know, maybe a certain number of like wave or of energy packets, right? These energy packets, and there's like a certain amount in there, right? And there's lots in that middle section. And then over here, you've got, well, you know, less, right? You've got these other wave packets. And then over in the ultraviolet side, you don't have very many at all. And that kind of makes sense, because when you heat something up, you're not going to really have many that actually reach that frequency, right? It's not hot enough. So you only have like maybe 2 or 3 or a few of those on that side, right? So that's kind of the idea, that you just have a lot more of these individual little packets of energy that are in this area. Now I drew this into 3 different sections, but really there'd be, you know, tons of these different little sections, right? But just to get an idea, hopefully that made sense. Okay, but the main takeaway from this is that energy itself is quantized, right? That's the big takeaway from this one. But, you know, that being said, this is what Planck suggested, just to fit the data. But even he didn't like the idea. He was even like trying for a lot of his career, because it just seemed too weird. He was trying to actually find more of a classical reasoning for it, because this is weird, right? Like if you think about it, like if you had like a certain amount of energy, you're saying that there's like a smallest amount of energy that you could ever have. Like, why can't I take that smallest amount of energy and then like divide it in half, right? Why can't I have half of that smallest amount of energy? But apparently you can't, right? That is quantum mechanics. That's the very smallest amount you can actually have, which is very weird. And everybody knew how weird it was at the time. Okay. Along comes Einstein into the picture, and he actually takes it another step and says, you know what? I don't think it's actually just the energy that's quantized. I think it's actually the light itself. So he took the formula, Planck's formula there, of E is equal to N times H times the frequency. And he said, well, this would also be true. E times N times Planck's constant. And then instead of an F, he wrote it as C over wavelength, which really just is because frequency is equal to the speed of light over wavelength, right? So he just replaced the F with C over wavelength there, essentially, and said it's actually light itself that's quantized. So if you've got some wavelength of light, let's say you've got like blue light. So Einstein was saying blue light only comes in these discrete little wave packets, right? So it's a different picture here, he's saying. So instead of it being, you know, light is these waves that we've been talking about, so you send these waves towards something, Einstein was saying, well, no, maybe it's actually the wave itself is a little packet. It can still be a wave, but it's like traveling in these little wave packets. It's like the smallest wave or packet it can be, or the like discrete little bundle there, right? Which again is a weird idea. So there's a guy named Gilbert Lewis. You don't really need to remember that one, but he introduced the term photon to describe one quantum of light, like one little particle or packet of light, right? So that's called a photon. Okay, so that's the main idea there. All right, so just a bit more about quantization and how this was revolutionary. And it took people a long time to actually get on board with this idea because it is so weird. It's like really. But you know, to tell you the truth, we've been dealing with quantization of things before this, right? Like like it was weird when we got to this point where when we were learning about charge, that there's a smallest charge you can have, right? That's that 1.6 times 10 to the negative 19 coulombs, right? That's the very smallest that a charge can be. So people were getting more okay with the idea of quantizing things because that really is quantized, right? You can't have smaller charge than that. That's as small as it gets. So they were, you know, people were a bit more comfortable with that idea. So it allowed for people to be a bit more comfortable. Well, maybe light is like that, and maybe energy is like that. So, yeah. Anyway, so there's no such thing as a half of an electron charge, right? Yeah. Okay. So yeah, a good little quote that Planck said. He says, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it." Right. So it kind of a bleak look on how knowledge is acquired, right? That you don't really convince people, just the old people die. Okay. Now, we're going to start using a new form of energy, or a new unit for energy, I should say, called the electron volt. And the reason why we're doing this is because, well, really because when we're dealing with quantum mechanics now, like all of our equations are at like the very, very small level. I don't want to use times 10 to the negative 19 all the time if I don't have to. So physicists came up with really essentially just a new unit of energy that was a lot more like a nice whole number that we could work with, right? And here's it, and it's called the electron volt. And where the electron volt comes from is that if you remember back to our electrostatics unit, if you had like these two charged plates, let's say, and you had an electron sitting on one, and let's say that you applied a voltage across those plates, then, and let's say 1 volt, so 1 volt across that plate, then it would accelerate that electron, let's say from this side to this side, if that's positive and that's negative. Okay. That's really the unit of energy that we're dealing with. They're saying that we're going to define an electron volt as the energy required to accelerate an electron through 1 electron volt, right? So yeah, so that's pretty much it. So we can say the amount, if you look at it this way up here, right, the amount of energy in joules, right, would be the charge, 1.6 times 10 to the 19 times 1 volt would give you this, right? So 1.6 times 10 to the negative 19 joules would be the energy that electron would gain, right? But what we say instead of saying 1.6 times 10 to the negative 19 coulombs, we're going to replace that with 1 E, right? 1 just E. And that is on your formula sheet too. You guys will see that there's like E is equal to 1.6 times 10 to the negative 19, right? So that's what we'll start using for our charge now. So something could have 1 E or 2 E or 3 E, right? And then you multiply that by 1 volt, then that would be 1 electron volt. Okay. It's not as bad as it sounds once you get used to it. So, in order for this to work out though, we actually, when we do questions, we can answer them either way. We can answer them in joules. Maybe the question wants joules for an answer, and maybe the question wants electron volts for an answer. Well, what you guys need to make sure you're doing when you read a question is that we're going to have different values for Planck's constant based on whether we're talking about joules or electron volts. And both of these forms of Planck's constant is on your formula sheet, right? So you just need to, it's on your data sheet, I should say. So you should just pick the one that's appropriate for the question, essentially. So we'll do a couple examples below, but, and yeah, make sure you guys look through these examples too if you're having trouble with the other ones, because they're good. But we'll do a couple quick practice problems and then that's it. So number 1, what's the energy of a quantum of radiation that has a frequency of that? Okay. So it says a quantum of radiation. So that would be like n is equal to 1, right? That's like just one wave packet. So in that case, we're going to say E is equal to Planck's constant times frequency. And by the way, this is the way that it's written on your formula sheet, but you should always remember that there really is like a little n sitting out front of that, right? It doesn't say E is equal to n times Planck's constant times frequency on your formula sheet, but you need to know that this is quantized, so there would be like 1, 2, 3, 4, everything else, right? So whatever you got to do, I don't know if you want to put like an n on there for now, so to help you remember it, but this is the true formula, but just the blue part is all that's on your formula sheet there. So anyway, just filling it in, we can say E is equal to, now, my answer is in joules, so it's expecting an answer in joules there. I already know what it is, right? So we're going to use Planck's constant that's in joules times joule seconds, right? So that would be that 6.63 times 10 to the negative 34 joules times seconds, and then times the frequency they gave us. So 3.45 times 10 to the 14 hertz. And that's equal to the number that they gave us there. I'll cheat. 2.29 times 10 to the negative 19 joules. Okay. So whenever you're given a frequency, you can figure out the corresponding energy from it, right? Because that frequency would just times Planck's constant, that gets you to your energy there. Okay. Now, it says a photon of energy of 5 electron volts. What is its wavelength? Okay, so photons are like light and energy. They're both quantized, right? We can actually use the same formula, but just the other version, right? The Einstein formula or version of it. So his version was E is equal to hc over wavelength. And this one's on your formula sheet, right? You guys do have that. Now, again, remembering, like if it's a different question, it's really n times that, right? Because it could be like 2 photons or 3 photons or 5 photons, whatever it might be, right? This one's just saying a photon. So that's like 1 photon. So I can just put a 1 in for n there. Okay, now, careful on this one. What do I put in for H? I got to put in the H one that has electron volts in it, right? I need the Planck's constant that has electron volts. So that one is 4.14 times 10 to the negative 15 electron volts times seconds. And then times speed of light is 3 times 10 to the 8 meters per second. Over, and then the wave, and then, oh yeah, sorry. Sorry guys, I gotta rearrange this first. Got ahead of myself. All right, rearranging this equation because we're looking for wavelength. Wavelength is equal to H times C over E. Okay, so same thing though. So now on the top, it's going to be 4.14 times 10 to the negative 15 electron volts times seconds, and then times 3 times 10 to the 8 meters per second, and then over, and then that's the 5 electron volts in the question, right? Now, just to see how this makes sense, right? Like we're looking for wavelength. I'm expecting my answer should be in meters, and it actually works out now. So with the units here, so I can see that I've got electron volts on the top, electron volts on the bottom. I've got seconds, and then seconds over here is really in the denominator, right? Because it's meters per second. So seconds cancel, and I'm just left with meters in the end, which is what I expected, right? So then in the end there, your answer would be 2.5 times 10 to the 14 hertz. Nope. Looking at the wrong one, trying to cheat and not getting away with it. 2.5 times 10 to the negative 7 meters.